This is part 2 of Riemann integrability. So if you have missed the part 1 video, just go and check where you can understand the basic concept graphically. Now we will see some theorems and some easy and important properties which will be helpful for problem solving, and we will see some problems also. Let us take one example to understand what Riemann integrability for the beginners. Okay. So this is the function h cube, and they have given f is a Riemann integrable on this interval. This is the notation, Riemann integrable on the interval a comma 0, and they have given f of h dx is integral over 0 to a equal to a power 4 by 4. This is very simple to know which is a Riemann integral or not. So when this has a value, then we can say this function is a Riemann integrable, that is this function is a Riemann integrable. So this is the basic proper definition for what is mean by a Riemann integrable. Now we will see some higher level questions. So coming to the question, this one, we should show an example that every bounded function need not to be a Riemann integrable function. So we have one of the property that every continuous functions are Riemann integrable and every bounded functions are so we have one property which we will see later, but I just write it down. So every continuous functions implies Riemann integrable. Every monotonic functions implies Riemann integrable. Okay, so this is the two cases that we should know. But here they have given, we have to show one counter example, that is every bounded function need not to be a Riemann integrable. So let us take a bounded function. So this is a such type of function where you will be having 0 if h is rational and 1 if h is irrational. So how this is actually, it is not coming as Riemann integrable. You should not say that this is not integrable, so it is not Riemann integrable. That is wrong. Okay, so firstly you should know that this function is not a Riemann integrable. You can just think about the graph. Okay, you have to think about it because we cannot able to write it down or plot it down. Okay, so what you have to do is, here they have said that this is not continuous function, and this is a bounded function because this range, the function is lying between 0 to 1. Okay, this function is lying between 0 to 1, so it is bounded obviously, and you are going to take any interval. A comma b can be any interval. It can be 0 to 1 or 0 to 2, whatever, a and b or some values. So you're just partitioning it, and what we have to do is, we are going to take the upper sum and lower sum. So this is what you got in upper sum, and this is upper sum. Upper sum is 1 and the lower sum becomes 0. So because you have 1 and 0 as a function, so upper sum will become 1 and lower sum becomes 0. Since this is not equal, this means that this is not a Riemann integrable. That's all. This is simple, but you should know what is mean by Riemann integrable. If the function is, this function is said to be a Dirichlet function, where they have defined for rational and irrational separately. So those functions are all Dirichlet functions. So we can find a function is Riemann integrable for. Here comes the necessary and sufficient condition for integrability. Integrability in the sense it is a Riemann integrability. Okay, so the necessary and sufficient implies, it means that it is a if and only if case. So you have to say that, I can read this sentence in the way that a function is said to be Riemann integrable. Integrability of a bounded function f is that to every epsilon greater than 0 that exists corresponds to delta, such that every partition P, the norm is less than or equal to, okay, this is the condition, UPF minus LPF is lesser than epsilon. So it is also can be written as f is said to be Riemann integrable if and only if this condition is getting satisfied, where epsilon should be greater than 0, there corresponds a delta greater than 0. Let's come to the bounded integrable functions, some particular classes. Okay, first theorem says every continuous function is Riemann integrable. Second theorem says a bounded function f is integrable in closed interval a comma b if the set of points of discontinuity is finite. Every continuous function is integrable, but every non-continuous function cannot be non-integrable. Some functions which are not continuous can also be integrable. We will see some examples. If you can't understand this statement right now, we will see some of the examples, right? So that you can understand that these points at that time. Okay. Now we will be having a bounded function f is integrable in closed interval if the set of its point of discontinuity has a finite number of limit points. So this one, and if f is monotonic in closed interval, then f is said to be Riemann integrable in that interval. So monotonic and continuous implies it is Riemann integrable. Before going to the sums, let us say some more important theorem statements. Okay, if f is integrable on this interval, closed interval, then f square is also integrable. So square of that function is also integrable. So these statements are all important for the multiple select questions in CSIR-NET. Okay, so just remember these statements also. You may use this for problem solving purpose also. So this is one of the theorem. If f is a bounded in this interval, capital M and small m are the infimum and supremum of f in that interval, then this relation holds. We already seen this in the part 1 of this video. I'll just show you. So this is what I have done in this part 1 of this video, where you can understand this Riemann integrability with graphically. So where you have come across with this point, where m times b minus a is less than or equal to LPF, that is lowest sum is less than or equal to upper sum, which is less than or equal to capital M times b minus a, and we have all these things. If you are not sure about the basic concept, you just go and watch it. Okay, then you can understand and you can be able to solve the problem by yourself. Now coming back to this theorem, here they have given m times b minus a is less than or equal to lower Riemann integral, which is less than or equal to upper Riemann integral, which is less than or equal to capital M times b minus a. So this is another one beautiful relation that you should know. Let's come to the question which is important for NET as well as JAM examinations. Here the question is given to be f of x is defined as greatest integer function x on this interval, closed interval. So they may ask whether this function is Riemann integrable or not. This is basic simple question. But they also ask to find the integral value. So for that is, you have to put integration and you have to find the value. Okay, so that is what we will be going to see now. So we have this greatest integer function x as a step function, because you know, in 0, 4 you will be having 4. Okay, now just listen. 0 to 1 you will be having it here. At 1 it is not 0, it is 1, right? So 1 to 2, at 2 it is not 0, sorry, at 2 it is not 1. So I'm just marking it with the round so that it means it is keeping that point alone. At 3 it should be 3, and at 4 it just need not to be at 4. Okay, this is the function, step function. This is greatest integer function on interval 0 to 4. So what you have is, this is the function and you have to integrate it. So in order to integrate, you have to integrate it, right? So for this 0 to 4, you will be splitting this function for 4 intervals: 0 to 1, 1 to 2, 2 to 3, 3 to 4. At 0 to 1, what is the function? At 0 to 1, the function is 0. So you will be putting 0 dx. That is, you are integrating 0. Then at 1 to 2 interval, you will be having 1. You need not to worry about the endpoints, okay? Then 2 to 3. 2 to 3, the function is 2. And 3 to 4, the function is 3. So you have to just, now it seems to be simple and you just have to integrate it. That's all. So this is one of the basic idea behind the Riemann integral. Now we will solve some higher level Riemann integral problem. It's the task to find the function is defined to be 1 by 2 the whole power n, where x lies between these two intervals. Otherwise 0, if it is 0, it is 0. So the function is it is not simple actually, but after solving it you may find it so simple. You should be aware that what is Riemann integrable. It means the function is integrable. That is, after integration you have to get some finite number, so that you can say the function is integrable. So this function is actually an integrable function. Two cases, that is whether f is Riemann integrable or not, then we have to find the integral of f is what for that particular interval. Okay, so these two cases we will be solving. After solving this question, I think you can able to attempt all the other NET examination questions as well as GATE examination question. And if you have any doubts, you just ask me in the comment section. Okay, here's the question: 1 by 2 the whole power n, and can we draw this diagram? I suggest you to draw every problem if it is possible. Okay, I'm just going to draw along with you. Okay, firstly you have to have this axis, and then they have defined x to be lies between 1 by 2 whole power n plus 1 and 1 by 2 the whole power n. So n takes the value 0, 1, 2, 3. So let us put n equal to 0. What happens when n is equal to 0? It means you are just going to do something. Okay, fine. If it is 0, what happens is 1 by 2 will be here, and 1 by 2 whole power 0. So it is 1. So what happens ultimately is, for 1 by 2 to 1, let us say, okay, let it be 1. Okay, so half will be in mid of this. Okay, so 1 by 2 to 1, the function takes the value as 1 by 2 the whole power n is 0, right? So 0, for 0, you have to substitute each and every value. So for 0, this range is coming and the value is 1 by 2 per 0, that is 1. Let it be 1. So let me change the color. No, let us first do it for this. For 1 also, because it is less than or equal to. Okay, it is taking this value, but it is less than, not equal to is there. So you have to put that count, indicating this is not a point of this domain value. For 1 by 2, it is not 1. Okay, we have to do another step function. Let it be in different color. So next you have to put n equal to 1. This is for, let me put it for your understanding purpose. So for n equal to 1, the range is between 1 by 2 power 2, that is 1 by 4. That is, I have to divide it in this way. So 1 by 4. Right, 1 by 4, 1 by 2, 3 by 4 will be coming. Okay, so 1 by 4 to 1 by 2. This is the range. Okay. So for this, this is the domain value. So 1 by 4 to 1 by 2, I'm just going to draw the function value. So sorry, I have mentioned the domain value. Okay, domain. Now I'm going to plot this value, that is 1 by 2 power 1. So that is half. Here it will be half. So half is taking the value, but 1 by 4 is not taking the value. So I'm just going to do this. So this is one function at n equal to 0, n equal to 1, and in this way it will be moving on and on and on. Okay, so this is the way you have to visualize this pattern. Here you have to put n equal to 0, 1, 2, everything. So you can understand where all the discontinuities are coming. So the discontinuities are the points at half, 1 by 2 the whole square, 1 by 2 the whole cube, and etc. So you can understand that these discontinuities are countable. Countable in the sense countably infinite. You can actually count it 1, 2, 3, etc. up to it is actually having 1, 2, 3, 4, etc. up to infinite cases. So totally it will be some infinity. And these are the countably infinite. So it is actually taking the natural number. So natural numbers, you have to know that natural numbers, rational numbers are all countably infinite. Whereas irrational number, r minus q, and r and complex number are all uncountably infinite. That is denoted by C, and this is denoted by aleph naught. Okay, so these are the extra informations alone, but you should know that this discontinuities are all quite countable. So when the discontinuities are quite countable, you have to say this is a Riemann integrable. So discontinuities can be finite, can be countably infinite, or there won't be no discontinuities. So here the discontinuities are countably infinite. So it is Riemann integrable. Okay, firstly we will see how this step function is being made, so that you have this graph right now. So you can visualize this, and you have to say that this is for bounded and monotonically increasing in 0, 1. It is integrable. So it is bounded plus monotonic. This implies it is integrable. So this is one of the main points that you have to note it. How to find the integral value? That is, we have to integrate the function. You have to take this function and integrate it. So this is quite tricky, as well as it is quite easy for you to understand also. Now your aim is to find the integral value, right? So you have list down the function value for the every intervals. So you have plotted from 0 to 1 how the function will be. In the previous sum you will have that greatest integer function. Now you are having this one. So there is no biggest difference. That's the definition. So you have to do one basic thing, that is you have to split the intervals. How this interval is splitting? 1 by 2 to 1, 1 by 2 square to 1 by 2. You cannot put 1 to 1 by 2 because you have to do it in the ascending order. So they have put 1 by 2 to 1. The function value is 1. 1 by 2 square to 1 by 2. The function value is 1 by 2. So 1 by 2 the whole cube to 1 by 2. So you have got this series, right? So what I'm going to do is I'm going to just subtract it this way. So this is half plus, so that you can able to sum it up, because this is an infinite series. You have to sum up anyways. So here I'm going to subtract it. I'm getting 1 by 2 square. Just be careful with the calculations and all. Here I'm going to subtract it. 2 minus 1 is 1 by 2 cube, and so on till I get 1 by 2 power n minus 1 times 1 by 2 power n minus 1 times 1 by 2 power n. Here it will be plus. So I think you are getting it right, because you know, the last term will be 1 by 2 power n minus 1, and I put it as it is. I just subtracted it. I got 1 by 2 power n. So in this way I got the series in this manner. So I'm going to find this very easily by using this GP. This is in GP. So A is nothing but half. The common ratio is 1 by 2 cube by 1 by 2. So 1 by 2 the whole square. So the sum of the series is A by 1 minus R. So this is the answer that you're going to get. So I'm going to take A to be 1 by 2 and R to be 1 by 2 square. So I'm going to get 1 by 2 by 3 by 4. So it will be 2 by 3. So this is the answer for this integral. You have to know that even this type of functions is also, we can find the integral value 2 by 3. So if you have any doubts in Riemann integrable, just ask me in the comment section. Thanks for watching.